Okay, so thank you for waiting. So it's a pleasure to have Professor Danilo Liarte from Cornell University. So he's going to be talking about geometry and disorder of soft matter. Thank you for coming.
Thank you very much. It's a great pleasure. I'm not a professor. I am a postdoc at Cornell. Thanks so much for coming and staying here. My name is Danilo Liarte, and I'm going to talk about geometry and disorder of soft matter. So let me start with a quote by Leo Tolstoy that I'm showing here at this corner sitting in his chair. And the quote is that he says that all happy families are alike, and each unhappy family is unhappy in its own way. So the basic idea that Tolstoy tried to argue for is that to be a happy family, you have to agree about several things. You have to agree about, I don't know, maybe money or children or religion, things like that. And if you fail to agree about one of these things, you are in this particular case of an unhappy family. And all of them are unhappy in its own way. There are many versions of this quote here, and I particularly like the one that says that all sane people are alike, and each crazy person is crazy in its own way. But I'm going to show you one that I don't know if it has been written down or not. And the quote is that all ordered systems are alike, and each disordered system is disordered in its own way. And this is very relevant for biology and physics in general. But the challenge that I'm going to expose here is that I'm going to try to challenge this Anna Karenina principle here. I'm going to talk about two systems. One of them is a Smectic liquid crystal that shows these beautiful patterns full of ellipses. Ellipses and hyperbolas and things like that. And I'm going to talk about jamming, which is quite ubiquitous, and how we can use random elastic networks to understand this jamming transition. So let me start with a brief outline of my talk. As I said, I'm going to talk about Smectics, about Martensites, jamming, and make some final remarks in the end. Let me start with the Smectics, and I'd like to first thank my collaborators in this part, Jim Cessna and Matt Beerbaum and Tai Coyne, Brian Leahy and Mujin Zhang. So imagine that you get this liquid crystal, which is a kind of a soap, and it turns out that Smectic is actually, the word Smectic comes from the Greek word for soap. You put the soap between glass slides, and you squeeze them, and you lower the temperature, and you observe them with a microscope. So this is the texture that you observe when you do this kind of experiment. Now look at these curves. It's quite impressive. This is failing. Okay. But look at the curves. It's quite impressive that, there you go. You can see very perfect shapes here. And I can actually draw an ellipse and put right above this figure. And there you go. You have an actual ellipse here, and you just put this liquid between glass slides, and you see ellipses, and you see these perfect geometrical shapes. And I'm also showing here this point here. Oh my God.
I think you're putting your finger on the front. It happens to 90.
Oh, I got it. Thank you very much. That's it. Got it. So you see this point here where there seems to be emanating some shadow rays here. This is actually one of the foci of the ellipses. So what's behind this kind of microstructure? What explains this kind of texture from this liquid crystal? So Georges Friedel, it's the second generation of a lineage of very renowned French scientists. Perhaps you know, for instance, Jacques Friedel, which is his grandson. He looked at this texture, and he knew a lot of geometry, and he could figure out what this Smectic structure was based on this texture. So the idea is that, imagine that you want to fill a space with a set of equally spaced surfaces. You can do that by stacking one plane on top of the other with equal spacing, right? And this would be like the ground state for the system. You can you keep filling space with more and more and more of these layers. And the line singularities that result by filling space with these structures are a pair of conics. They are an ellipse that I'm showing here, and a hyperbola. And the vertex of the hyperbola crosses right through one of the foci of the ellipse. So that's the reason why you can see one of the foci. It's a singular point. So you do the experiment and you can see it. And you can see the ellipse because it's singular there. So today we know the textbook picture of this Smectic liquid crystal. You have this layered structure, and inside each layer you have some liquid-like behavior. The molecules are arranged here, for instance. But Friedel was the guy who could describe these very beautiful geometrical defects because he knew a lot of geometry. Yeah.
This is singular in what sense? The density goes to...
I'm giving you an example in which sense it's singular, for instance. Imagine that you have a set of concentric spheres and you pass rays or straight lines that are normal to the spheres everywhere. They will all converge to a point, which is the center. So it's singular in this sense. You can do the same thing with the other surfaces. You can pass a straight line that's normal to the surface everywhere, and they will converge in this singular point. And if you look at the shape of the layers themselves, they are like pinched off from the singular lines.
So these geometrical surfaces, they're important, they're formed because they minimize some energy or something like that. What's the physics behind this geometry?
That's correct. There is an elastic energy that's kind of phenomenological that in some sense explains why the system likes to form layers. It breaks some symmetry. There is a phase transition. So the point is that you have a liquid crystal, and a liquid crystal in general, you have these molecules that has elongated shapes, for instance. The simplest case is a nematic liquid crystal, and you put them together, and you can, for instance, decrease the temperature or increase the pressure or do something like that, and they will like to align because they are elongated. I can try to draw that. You have these elongated shapes. So if the temperature is low, they will like to align. It broke asymmetry. And if you lower the temperature further, they will start forming layers so that they can pack together more closely.
But in the case of the salt that you described first,
Yes.
there's some energy function that is minimized by the shape that they acquire.
That's right. That's right. They like to form layers. That's the basic energy function that it minimizes. I'm going to show right in 2 clicks what this free energy is. I'm not going to express it explicitly, but it has some energy costs associated with the distortion of the layer spacing and other things. I'm going to get back to that. So we want to simulate these structures. These structures are quite beautiful. We want to see them in the computer, for instance. So what we do is that we start with some elasticity theory. We define a vector field that's normal to the layer everywhere and whose size is associated with the size of the spacing between the layers. So we define this field and we do a simple dynamics. It's a gradient descent dynamics. It's just given by this equation. This is quite general. The time derivative of this layer normal field is minus the functional derivative of some elastic free energy with respect to this layer normal field. And this layer and this free energy you can express for this Smectic case, for instance, as a sum of three terms. One of them that penalizes the compression and the extension of the layers. That's what I was telling you about. And there are other terms that penalize the bending of the layers. There is a term that's associated with the mean curvature and the Gaussian curvature of the layers, for instance. So we do that. We put that in the computer, we discretize, and we run simulations on that. We start with some random initial configuration and solve for the dynamics based on this equation here and this free energy here for this layer normal field. Say that again?
Where does that first equation?
This is just telling you that the system is going towards a low energy configuration. So this is, if you wish, there is a Langevin equation, for instance, but that would have a disorder term. This is just a gradient descent dynamics. As you can see here, this will be minimized when you are at the minimum of the free energy.
There's no coefficients or nothing?
I can choose the coefficients. Of course, you could have something that works like a viscosity there, but I can choose the units so that they don't appear in the equation. Yeah. So we can simulate that. And I'm just showing here one slice of such simulation. We start with some random initial configuration. It's a three-dimensional simulation, but I'm choosing to show you here one of these slices where the layers are perpendicular to the section that we are looking at. And as you can see, you can see the formation of things that look pretty much like the focal conic domains that I have described to you before. Now this is nice, but the big advantage, in my opinion, of having simulations to describe these systems is that you can actually see it. You can actually probe into the inside of your full structure from the simulation results. You can plot, for instance, you can use some volume rendering technique and plot the energy density as a function of space in general. You can do some sort of three-dimensional plot. And here, the red regions are the regions where the energy density is high. It's where the singularities are. And you can see the ellipses and the hyperbolas coming out of the foci of the ellipses. There's a pack of them there.
Sorry, can you show the forms for these functions that you use for the simulations?
I can show you. I can show you one of them. One of them will be complicated. But for instance, I have FB here. Let me write down it again. This is the functional free energy. There are three terms, FB, Fs, and Fs. SS. So this FB here in our model is 1 minus n to the fourth. We choose the layer space to be 1, so we wanted to have an energy that penalizes anything that...
So is this chosen by hand?
This is chosen so that it describes correctly some of the results, yes.
You try different forms, and this is the one that works?
We have, for instance, 3 different models that we can use, and they will differ more or less in the dynamical properties, which is not what we're looking at. We will be looking at right here. But they have the same kind of, they minimize towards the same kind of minimum configuration.
But can you understand this in terms of interactions of these n vectors with each other?
So this is like a field theory that goes beyond the microscopic interaction between the elements, the molecules. Yeah. Yeah, so this is one term, and
That's okay.
Okay. The other terms will depend on the gradients. So it's like a Ginzburg-Landau theory in superconductivity, for instance. So you can do that. You can plot the energy density. You can reconstruct the layers. I've defined this dynamics in terms of this layer normal field, but you can go a step back and reconstruct the layers, and you can look at them. And if you have the layers, you can calculate stuff with them. You can calculate the centers of curvature, and the centers of curvature have to be right at the singular lines. And you can check if that happens. We calculate it, yeah. You're supposed to see it. I suppose the figure in the computer or in the paper is clearer then, but you have lots of layers here.
Can you rotate it so I can see it?
I can't rotate it right now, but I can rotate it in Mathematica if it's, yeah. But yeah, in principle, I can select one focal conic domain more or less and then rotate and look into the insides. Unfortunately, I don't have this tool here to show you. Yeah, so you can calculate the centers of curvature, and they lie exactly at the singular lines as they should be for a focal conic domain. And you can do like microscopy images, something mimicking microscopy as I've shown you before. So you have all these visualization tools, but you can do more than that. You can imagine a situation, for instance, where you have a set of layers, Smectic layers, one on top of the other. They are between glass slides, and you increase the gap between the glass slides. And you do that, the layer spacing will start increasing, but the system doesn't like the layer space to increase. So at some point, the energy is going up, 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 and there is an instability, and the system buckles. And that's shown here by this picture here of the layers, of some cross-section figure of the layers themselves. The system buckles. There is a buckling instability here that's captured by our simulation. And we can do calculations based on that free energy that I showed you before. And they agree pretty well with the simulation result. If you continue going up in energy and continue increasing the gap,
What are the calculations?
linear stability analysis. Yeah. And then if you continue to increase the gap, at some point here there will be another stability and there will be an array of focal conic domains. And that will decrease the energy again. And at least in this protocol that I'm considering, I'm going up, 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 up until some point and going down back to where I was at the beginning. This is the free energy profile. This is the texture when you have this array of focal conic domains. And it agrees pretty well with experiments performed by Itai Cohen's group in Cornell. So we have the simulation that do all of that. And I can show you just a section showing this whole protocol going on, but there's not much to be seen here.
Sorry, let me just understand something. So you showed already two movies.
Yeah.
The end point was trivial again. At the very end, the movie becomes trivial, right?
That's correct in this case.
And in the previous, was it also the case that the
No.
circles were becoming bigger?
That was different. That was, it starts with a random initial configuration and evolve in time until the focal conic domains will coarsen and grow and evolve towards some equilibrium configuration. And at the end, it just starts back from where it began.
So it reached an equilibrium where they had some typical size?
I didn't show you that movie. We didn't go all the way towards equilibrium.
But if you did, would it have some length scale? Would it be scaling?
It would. Yeah, there are two important length scales here. One is the layer spacing, and you can control, for instance, the length scale associated with the layer spacing by controlling the coefficients of these two terms here.
Yeah, maybe it helps me if you write. So you mentioned the words Landau-Ginzburg. Should I take those words at face value or more or less?
You should take in the sense that you have a functional free energy that depends on the order parameter and derivatives of the order parameter. That's all the sensitivity.
Right, so some terms should be relevant, some should be irrelevant, right, for studying the equilibrium configuration.
That's right. I'm just writing down the relevant terms, yes.
So for example, you have n to the 4, not n squared,
That's right. We can use n squared as well. That's one of the models that we can consider.
but it will give probably the same, no?
It gives the more or less the same kind of result.
Because you are expanding around 1.
That's right. Yeah, so the derivative, for instance, this term here is something like k over 2 div n square.
And the last one?
Oh, the last one is complicated, and I will not be able to write it down all of.
But so far, this is like 3D Ising model, right?
This is not like 3D Ising model.
No?
No. I mean, I don't have coefficients there in this expansion here that looks like m squared plus bm fourth. I don't have control over the coefficients here, for instance.
Right, so it's
And
at
there's-
fixed temperature and magnetic field.
And this is a vector field.
So it's ON, so it's Potts model at fixed temperature and magnetic field. It's ON, it's the vector model at fixed temperature and magnetic field.
I'm not sure if it has the same symmetry.
Okay, so maybe we should see the last term. So what's the last
Oh, yeah. So the last term is a KSS. And then it is a total divergence term, and I cannot write it down explicitly right here at the top of my head, but there is some combinations of n's and grads here that I do not remember right at the top of my head.
With how many derivatives?
2 derivatives.
And 2 n's?
And 2 n's, exactly.
Then by the equations of motion, it will be equivalent to the first one, a mixture of the
No,
first.
it's not equivalent to the first one.
So the last term seems to be what?
So yeah,
That's one, right?
the last term is like, has a term, this is a splay term in the language of liquid crystals.
It's what?
Splay,
I don't know this.
this word comes from this deformation here, for instance. This is like splay. So this is what penalizes this kind of deformation. The splay term, and this is a pseudo splay term. The pseudo splay term has a component that looks like a splay term and something else. It's not just a splay term. I can show you offline if you wish, but they are not the same thing.
Let me ask differently. Should I think that in equilibrium, I'm studying statistical mechanics with some Lagrangian, right? Is it true or not? If I'm at equilibrium, I'm just studying statistical mechanics.
Yes.
Then there are universality classes, right? Where many models in statistical mechanics fall in the same universality.
That's right.
So on which universality class is this model on?
I'm not studying the transition here. I'm not interested in the universality class.
So you're interested in the gap phase.
I'm interested in the phase itself.
The gap phase and the gap.
What do you mean by gap phase?
It's not critical, right? So it's not the phase transition, as you are saying.
Yes,
So
I'm not
correlation
looking into the
line is
phase
finite.
transition, yes.
So you have a finite correlation line, and that's why you don't have universality.
Yes, if you wish. I'm not close to a critical point here. I'm deep into the Smectic phase. I'm not looking to the transition. Okay? So, I started by showing you this very beautiful texture, and I've given the geometric interpretation that's behind this kind of two-dimensional texture. And we now have some simulations for that agree pretty well with some experiments that are performed in these phases. But there's a question of not only you have one focal conic domains, but how you group them together, and how you look into these regions here that do not seem to form ellipses or hyperbolas or anything. What are they? And how can we interpret them using the same kind of methodology? And this is the theme of the second part of my talk, which is about Martensites. So before I go there, if there are any questions, maybe that's a good time to pause and ask for questions.
So I'll talk about, so is it fair to say that mathematically we are studying this model, right?
Yes?
So it would be very nice to know what these terms are, because otherwise I don't have intuition why things are curved. It's very hard to have an intuition if you don't try to. What is, for example, grad dot n is del 1 n1 plus del 2 n2, or is
Let me.
Could you try to spell that?
Oh, this is div n.
I would just like to know what Lagrangian we are studying if we are going to discuss a Lagrangian. If we are discussing a theory, can we write down the theory? Or can you give some intuition of what these terms do?
Sure.
These terms, you were drawing some pictures, for example.
Yes. For instance, imagine that you have some layers.
Okay.
So this term here is penalizing the bending of the layers.
Yes.
Right?
Yes.
So this is associated with the mean curvature of the surfaces. You know, you can write down two principal curvatures, and you can take the arithmetic average or the geometric average, and one is the mean, the other is the Gaussian curvature. This penalizes the mean curvature of the layers. And this term here that I don't think it's necessary that I remember exactly what it looks like. I mean, I don't remember exactly the whole formula for it here, but it penalizes the Gaussian curvature of the layer. So it's like you know that the...
Yeah, can you remind me?
Yes, for instance, imagine that you have a surface. Let me see. If you have a surface like this, and so I didn't expect to show all this geometry here. You have, for instance, at this point here, you can pass a tangent plane to this surface. That's unique. And then you can define a set of normal planes, and then you have infinite of them, an infinite number of them, normal planes. So imagine that you pass these normal planes here, and there is the intersection between the normal planes and the surface, and you can calculate the curvature for each one of these intersections and get the maximum and minimum value of the curvature. These are the two principal curvatures. So this play term is associated with, if you calculate the curvature, with, say, K1 plus K2 over 2. And the other guy will be proportional to K1 times K2, which is the Gaussian curvature. So there might be a surface, for instance, that has positive Gaussian curvature because the two curvatures are positive, like this one. Or you can have something that's like a saddle that has a negative Gaussian curvature, where one is positive and the other is negative. So these are the kind of terms that appear in the free energy of the Smectic case that I'm showing.
Then, based on this intuition, can you immediately argue that this kappa is much bigger than kappa SS? I will have cylindrical shapes versus spheres and things like this. Because say cylinders will have K1 equals 0, but spheres will have both curvatures.
Yeah. So the Gaussian term here, the term that's proportional to the Gaussian curvature is important right near the line singularities. So this term, it's another important thing here that you can get some intuition for is that this is a total divergence. So in principle, it only matters at the boundary of your system. because it's just a derivative here. You can use something like Gauss theorem. And if you use, for instance, periodic boundary condition, that should be 0. So we have a trick to deal with this, which is basically to have some dependence of this moduli here, this modulus here, on the size of the layer spacing. It's something like near the singularities. Imagine that you have the singularity here. We have to have the order parameter that goes to 0 here near the singularity in order to have a well-defined behavior for this free energy and things like that. But I mean, you're trying to frame this in terms of critical phenomena, and it's not about that. It's about, you can understand that there is energy cost to deform the layers, and that's what's represented here.
No, I understand. I just want to understand what's the energy function. But okay, I think you explained.
Okay, so I'm going to talk about Martensites now, and these are my collaborators in this part of the project. Jim Sethman, Matt Beerbaum, and Randall Kamen, and Ricardo Mosnam. So let me start by giving you a brief intuition about what a Martensitic transformation is. And what I have here,
Sorry,
yes?
What was the first term doing? Can you remind me?
Yes, so the size of this vector is associated with the size of the layer spacing. So I want the layer spacing to be fixed. So it's fixed to unit here by this first term. So imagine that you have a crystal. That's a little bit different from what I've been showing you before. And at some high temperature, you have a global minimum for this crystal, which corresponds to this austenite phase, where it has a cubic shape, a simple cubic shape. And you lower the temperature, and the crystal likes to deform along one of the 3 Cartesian directions. And there is a phase transition here between an austenite phase to a Martensitic phase, where you have 3 distinct minima for this free energy landscape. Now imagine that you do this experiment with your crystal while constraining the boundary conditions so that the net strain doesn't change. So you not allow the whole material to elongate in some distance. It's fixed. What will happen is that these variants, these 3 different variants some regions will like to deform along one direction, some regions will deform along another direction. And these variants will rotate, form these string boundaries, forming these fine laminates that are shown here. So what I'm going to show you next, in the next slides of this part, is that you can see the Smectic microstructure as a kind of Martensite, and how you can interpret them as a Martensite. Smectic is a word for a liquid crystal phase, with what I've shown you before, right? So that's a Smectic. So Martensite is, I've just given you an example of a Martensitic transformation. A crystal that has, for instance, a set of energy minima and coexistence of different phases, for instance, is a Martensite like this. Okay? So did you follow the Martensitic transformation? That's the important word, right? So there are 3 ingredients that I'm going to talk about from the theory of Martensites that I'm going to use to describe this Smectic microstructure. One of them is the variance. And I'm showing here the 3 crystal martensite variants correspond to deformations along the 3 Cartesian directions. And you can, for instance, describe these deformations by distortion tensors. You don't have to be worried about these formulas. But each distortion tensor here is associated to one of these deformations. That's right. I've chosen one Martensite transformation where it's kept constant. And that's why you have eta square, eta minus 1, and minus 1 there, so that the determinant is 1. So the volume is kept constant. So these are the variants for the crystal Martensite. For the Smectics, we choose the variants to be this 3-dimensional toroidal focal conic domain. I had shown you before another kind of focal conic domain where you have an ellipse and a hyperbola. But you can think of a simpler case where you just have a circle and a straight line. The ellipse becomes the circle and the hyperbola becomes a straight line passing through its center. And the layers themselves are a set of tori that wrap around this singular circle. And they can be described as levels of these functions here. And you can have, for instance, 2 signs for these functions. You can have a plus sign and a minus sign. And these will be the 2 variants that I'll consider for this Smectic case. So any layer can be described by a constant value of this phi plus here, or the phi minus here. And now if you want to simplify it and look into the 2-dimensional case, for instance, for the Martensite case, in 2 dimensions, you have 2 variants, one that's elongated along the vertical direction, and the other that's elongated along the horizontal direction. You want to know what eta is? Okay. No, okay. I mean, I should have brought the details, but in elasticity theory, for instance, you have something that you call a reference and a target space. You start with a reference space. The body is undeformed, right? And you can describe it by a set of coordinates, each point of them. And I'm going to call this x, right? And then you deform this guy. And each point here will be brought by a displacement vector, u. And then there is a set of coordinates in target space, which I call y. So the u matrices here are just dy, dx. It means that it's a matrix. Like, I mean, there are 3 coordinates here, right? There is, if I change the notation, there is Rx, Ry, Rz, and then this in reference space and in target space. And you take 9 derivatives, and what I'm showing here is a diagonal matrix with eigenvalues eta squared, eta to minus 1, eta to minus 1.
What I don't understand is you wanted me to a different deformation, but it looks like if I just change eta to eta inverse, they're the same. So why tell me different?
If you just change eta to eta.
You wanted U2.
Huh?
You wanted U2. I'm just looking at your 2 different deformations. And that's why they're different.
Because they are along different axes. You can imagine, for instance, a crystal that has anisotropic properties. So the deforming along one axis is different from deforming along another axis.
Are you assuming 8 is bigger than 1?
It can be bigger or can be smaller than 1. This is general for a certain deformation. Imagine this eta to be fixed.
I'm just trying to understand. You know U1 and U2, right?
Yes.
If I just change what I'm calling eta to eta inverse, U1 becomes U2.
But that's not it. What I'm describing here is something like that. You start with this guy, and if you calculate this matrix for a certain deformation, you have one variant that's a deformation along this x, and one that's deformation along that corresponds to this guy. And U1 corresponds to, for instance, this guy, and U2 corresponds to this guy. You don't have to.
We can discuss later. It looks like you're assuming A is bigger than 1. We can discuss later.
That's right. I mean, I was talking in general. But if you have a deformation, a distortion of this kind, an extension of this kind, eta is bigger than 1. Oh, sorry, if that's what you're concerned about. So for the two-dimensional case, if you focus, for instance, your attention in this particular case, in the plane of the singular circle, for instance, you can describe, for instance, the layers simply by levels of conic surfaces. And I'm showing two different conic surfaces here with different signs, one with a positive sign and one with a negative sign. So you can imagine that just by going up in this surface, in this hypersurface, you can describe the layers of the system in this 2+1 dimensional case. So now there's a very interesting connection between Smectics and special relativity. And the fact is that this has been discovered by a group at the University of Pennsylvania. The point is that you can see, for instance, d-dimensional domains as level sets of hypersurface in d+1 dimensional Minkowski space. So let me just give one step forward. I've shown you before these things that looked like light cones. So you can describe your Smectic layers by these cones. And the fact that you have this conic surface here, if you take the gradient of this function, the gradient of this constant function is constant the same way that the speed of light is constant in special relativity. So the equal space constraint is actually equivalent to the light-like hypersurface in Minkowski space. And you can see this phi function here as a time-like direction. So you can imagine, for instance, applying a Lorentz boost in your Smectic liquid crystal. And in relativity, if you apply a Lorentz boost, the speed of light is the same for all reference frames. In the Smectic case, you can apply Lorentz boost and the spacing constraint is maintained. The Lorentz transformation will preserve the null space, null surface, but not the level sets. What a Lorentz boost will do is to actually change the toroidal focal conic domain from this toroidal shape into this elliptic hyperbolic shape. So this is an interesting connection between Smectics and relativities, and it leads us to the third part of the theory of Martensites, which are the energy minimizers. And for the crystal Martensites, you can usually, after you have your three variants, you can rotate them and apply some general three-dimensional rotation, and you still have a minimum of the free energy. For the Smectic, you have a much richer group of symmetry. You can not only rotate them, you can apply a dilatation on your Smectic. You can apply a boost, and then you change your shape from this toroidal shape to this elliptic hyperbolic shape. You can apply a 3+1 dimensional translation. The group of symmetry that minimize the energy for this Smectic is this Weil-Poincaré group. It's Poincaré group plus dilatations. And now, again, if you focus your attention to the simpler 2+1 dimensional case, what you have, for instance, is just a translation group in 2+1 dimensions. You can translate the event associated with each light cone in this XY direction and the time-like direction for this Smectic. So the last ingredient of the theory of Martensites is the compatibility condition. I've shown you before how the variants of the Martensites will rotate and form twin boundaries and form these fine laminates in order to minimize the free energy while you have some constraining boundary conditions. Now, for the Smectic case, in order to find, for instance, for the 2+1 dimensional case, in order to find the compatible condition between two different variants of the Smectic, you have to find the intersection between cones. And I'm showing here two different cases. One where the two cones have the same sign, a plus sign, for instance. And if you look at this figure, you can convince yourself that this will look pretty much like a hyperbola, the intersection between the two cones. And in the other case, if you have a plus and a minus sign, if you look at the intersection, they'll form an ellipse. And you can derive, for instance, the intersection between these based on the parameters of the translation group of symmetry. And this is the equation. You don't have to pay too much attention to it. But it describes these compatibility conditions and it generalizes these twin boundaries compatibility conditions in the Martensite case. So I have started this part of the talk by showing you this crystal Martensite microstructure. And now we have a Smectic microstructure, and there is a lot going on there. So let me go slowly over this. I'm showing here the layers. I'm looking at a section of the Smectic where the layers are perpendicular to the section that I'm looking at. So you can see the layers here. The colors are chosen based on the parameters associated with the translational group of symmetry. So for each region, we use a clustering algorithm to decompose the space into these different variants. And I'm also showing here the compatibility conditions that I derived before and that agrees pretty well with the microstructure that we have found, for instance. So this generalizes this applies, for instance, the theory of Martensite to understand and explain the Smectic microstructure. So are there any questions about this part of the talk?
I think I'm totally lost. Where are the boosts coming from in SOAP? I thought we were starting to step SOAP, then there are boosts and relativity. I think I got totally lost with the logic. What's the connection between space-time relativity and the problem we were trying to solve? Or did we change problem?
I'm not. Bring it down a little bit just to one question. What's the question that you want to ask?
Well, where are all these special relativity, space-time symmetries? Why are they related to the problem we started with? We started solving a minimization of soaps, right? Films.
Yeah.
Am I right? And then we had some symmetry.
Wait, yes, I'm looking now at.
I missed the connection.
So at one point I was showing the simulation results that we had.
Yes.
That used, for instance, that elastic free energy.
Right.
And now you get at a configuration for this Smectic, say a final configuration for this Smectic,
Okay, good.
right? And then you apply this methodology, this theory of Martensites, and special relativity, and Lorentz boosts, and all this stuff to explain how this microstructure, how the different focal conic domains combine themselves, and how you can explain this microstructure of this Smectic.
I'll ask you after. I'm a bit, is it because they are ellipses? No.
Why is because there are ellipses?
So So we found some final shape, right?
Yes.
We were sure. Okay, so we have those final shapes. On the other hand, we have some group theory that you explain, more mathematical, some transformation rules that form some algebra. How did you connect the two subjects? I did not understand the connection between the two subjects. The shapes that you find in a simulation and the algebra, the conformal rule. How did you connect them?
Yeah, so we are applying this theory of Martensites. I gave 3 ingredients. You start with variants. So you describe each region, for instance, by a 1 variant. But you can also apply a general symmetry transformation to this region that doesn't change the energy, for instance. And that's where the symmetry group enters. For the Martensite case, you just rotate the variants and combine the different variants by rotating the variants. For the Smectic case, you have this richer group of symmetry. You can apply a Y-Poincare transformation and combine these different regions with different Y-Poincare transformations together. And that's what forms this mosaic that I showed before. These are different regions that are associated with different parameters of the Y-Poincare transformation. They form clusters.
So this Lagrangian had more symmetry than we would naively get.
So I don't really need to connect the Lagrangian now to this final shape. Imagine that just that you have the final structure. The energy that it minimized before doesn't matter. It's just the microstructure, all the structure that you have in the end. I'm just looking at one time and looking at the structure and explaining the structure, what the structure is about. Okay? So let me go to, maybe we can discuss more offline. Let me go to the last part of my talk. Oops. It's about jamming. And I'd like to start again by thanking my collaborators, Tom Lubensky, Xiaoming Mao, and Olaf Steno. So here I start with the jamming protocol, a protocol that will give rise to a jammed configuration. Just to explain what this is all about. So imagine that you have a plane, and you start with disks separated in this plane. And you start increasing the radii of the disks until they touch. And after they touch, you just stop. And you keep doing that for all of the disks in your plane. And at some point, all the disks will stop. Then you shake it a little bit, you move it a little bit, there will be some white space that they can use, and you start growing them again. And you repeat this process over and over again until at some point the disks will be so interconnected that you cannot move them anymore. So you have reached a jammed configuration. So this is an example of a protocol leading to a jamming configuration. And I'm showing here one of them. So this was actually done in a computer to produce this jammed configuration. One of the interesting things about this is that you can build, for instance, the network of contacts between these spheres or these disks. And it looks pretty much like this. You can count, for instance, the number of contacts for each one of them. Some of them, for instance, for this guy, oops. This guy here has 4 contacts. This guy has 4. Some will have 3. Some will have 5. I don't know. The average number will be 4. And there's a good reason for it to be 4. 4 is 2 times the dimension. And there's an argument that has been given by Maxwell that if you count the number of floppy modes, the number of modes of deformation that doesn't cost any energy, that this number of flop modes is given by, you can use an accounting argument, and it's given by the number of degrees of freedom, which is just the dimension here, minus the number of constraints. And the numbers of constraints is this average number of this number of contacts divided by 2, because you have a double counting here. These two disks have the same constraint. So when the number of flop modes is 0, based on this counting argument that's very simple, you reach mechanical stability. So VC, the critical, the isostatic point, and I'd like you to remember this name, isostatic, because I might use it later. Is this point where you reach mechanical stability. So in elasticity theory, you describe deformations, for instance, with elastic moduli. You have deformations that involve changes in the volume, for instance. These are described by a bulk modulus, and deformations that doesn't involve a change in volume, which are described by this shear modulus. And in the jamming transition, you can think of a phase transition where the connectivity jumps from 0 to some value for the bulk modulus. So there is a first order phase transition for the bulk modulus, and grows continuously as you increase the connectivity for the shear modulus. So this is a typical example of a jamming transition. Now, these jamming transitions are quite general, and you might be asking yourself, why do you care about these disks or spheres touching themselves and get jamming? Of course, you care about them if you care about granular media, but that's kind of obvious. There are much more than that, and I have named this slide ubiquitous jamming, so it suggests that there are many systems that can be described by this kind of phase transition. So you care about that, for instance, if you care about cell tissue. And there's a model, for instance, for cell tissue, where there's a fluid to solid phase, and I'm not going to give you the details here. This has been published by Max Beep and Lisa Manning from Syracuse. And in this transition here, there is a region here, a fluid phase which is dominated by cell-to-cell adhesion, and a region here that's dominated by cortical tension. And there is a transition that's pretty much described by this jamming transition that I just described to you. And again, I don't want you to be concerned about these particular formulas here. This is a scaling collapse, the kind that's used to describe critical phenomena in general. And it's a signature of a certain universality for the jamming transition. So this model, this biological system, is described by a jamming transition as well. But it's much more than that, and I'm going to just list some of them. You can use them for allosteric regulation, molecular glasses, colloids, space, emulsions, foams, and even dislocation systems. So jamming is actually everywhere. But jamming is not only ubiquitous, it's also very unusual. And I'm showing back again the network of contacts. And there is a lattice, for instance, that I remember of when I look at this picture with these triangles here. You can think of something that looks like a Kagelman lattice that I'm showing here. It also has something like triangles here and there. And I'm even going to cheat a little bit and draw some red lines that look pretty much like this cluster here that I'm showing, and some green lines here connecting next nearest neighbors, just to cheat, that show that you can get something with a topology that looks pretty much like a jammed lattice. B is the bulk modulus. In elasticity theory, you describe, for instance, an expansion of the free energy in terms of powers of the strain, and you can separate the deformations that are associated with changing volumes. The coefficient for this deformation is the bulk modulus, which is B, and G is the coefficients for deformations associated with shear. Okay?
touching? Or, I mean, are they perfect circles, or are they not perfect circles?
No, I mean, yeah, they are touching. I mean, this is done in the computer, for instance, and you have to have a threshold for when they are touching or not.
So what's the threshold? That's what I'm asking.
I mean, this is arbitrary. You can choose the threshold to be as small as the computer can manage.
No, that's not true. I mean, if the threshold is very, very small, then you may lose some contact.
No, the idea is that this is for spheres touching each other. And there are...
What's the flexibility? When you say touch, I mean, if it has a radius 1, does it have a radius 1 or 1 plus epsilon, where epsilon is small? That's what I'm trying to ask.
You want to know what epsilon is chosen for this case?
Well, I would think you want epsilon equals 0.
Yeah, but in the computer you cannot use epsilon equals...
What I'm asking is, if you change epsilon, does the number change? Because if epsilon goes
Oh.
to 0, you may lose some contact.
I don't think the number changes very much if you change epsilon, just by a little bit, but at least for the applications that you are interested in.
I would think as you take epsilon to 0, you start to lose contact.
Take epsilon to 0. Yeah, no. I mean, there are some technicalities involved in getting this jammed configuration that I'm not... Yes. In principle, I think there is a way, for instance, that people do that they let the spheres cross each other a little bit, and then they come back so that they just touch. You understand what I'm saying?
Yeah, that's what I'm asking. So, I mean, there's a mathematical answer, which is epsilon equals 0.
Yeah,
And then there's some physics answer where epsilon is something else.
yeah,
I guess that the value of epsilon is relative because we're doing physics, not mathematics.
yeah. But what I'm saying is that I don't think it changed very much for the values of epsilon that we consider in this case. You check epsilon to be 10 to the minus 8, and that's it, I mean. So some people might have thought that you could start with an isostatic lattice, a lattice that satisfies this Maxwell constraint argument. And you have, for instance, in the Kagome lattice, you have 4 contacts, which is actually equal to 2 times the dimension, which is exactly the isostatic limit. So you could dilute some bonds and add some bonds in some random way, in some precisely described way, and study the transition between rigidity from a fluid to a rigid phase. And they find out that they can describe, for instance, a bulk and a shear modulus for a system like this, and they have done for other lattices as well. And it has a transition that has a bulk and a shear modulus that goes to 0 at the rigid percolation transition. Now, rigid percolation is different from jamming in an important way, and that's what I'm trying to emphasize here. In jamming, you have this kind of unusual behavior where you have something that looks like a first-order phase transition and something that's like a second-order phase transition. Whereas in this general rigid percolation case, you have something that has mixture properties of first and second-order phase transitions. So to have a model starting from a random elastic network that gives rise to the right properties of jamming, you have to start with other kinds of lattices. And the kind of lattices that give these properties are these under-coordinated lattices. Here you have, for instance, the honeycomb lattice and the diamond lattice. And the honeycomb has 3 contacts per site, whereas the diamond lattice has 4 contacts per site. They are below the limit of connectivity that you need to have stability, mechanical stability, so they are under-coordinated. Now, the model that we consider that gives a genuine description of this jamming transition is a model, for instance, where you have 3 sublattices, and that's what I'm showing here. You have a honeycomb lattice here that's shown by these green bonds, and each of these bonds is populated with a probability distribution, populated with a probability PA. and then two triangular lattices, the blue and the red triangles here, again with each bond populated with probability PB and PC. And you can imagine having something that's similar to that, but now in 3 dimensions, you have a diamond lattice, and it's a little bit trickier to visualize this. Now, you can do simulations, for instance. You can build these lattices in the computer and do simulations for that using the prescription that I just gave you for building the lattices. You can do experiments. You can 3D print each of these lattices, for instance. But the nice thing about these random elastic networks is that you can actually use effective median theory and actually solve for the properties of these lattices. And I'm not going to give you, I'm going to skip the details again. In the effective median theory, you have a set of effective spring constants, Ka, Kb, and Kc, and they satisfy a set of equations, self-consistent equations, that will depend also on the 3 probabilities and on frequency as well. So you have a pretty robust description of the whole Jam transition, including dynamical behavior. So you solve for these equations here as a function of PA, PB, and PC, and that can give you the properties, the critical properties of the jamming transition, as I'm going to show you in the next slide. Just to anticipate a little bit, for instance, you can do scaling collapse plots. Those are signatures of phase transitions, for instance. And I'm showing symbols here that correspond to scaling collapses plots near the jamming point, and some analytical curves that you can find from this effective median theory. And the important thing is that the shear modulus, for instance, for jamming satisfies exactly the same kind of critical behavior that you observe here, and that we have an analytically tractable model that you can use to describe this jamming transition. Now, this is the phase diagram of our system, and that there are lots of phases here. There is a flop phase that's behind this blue region, and in our effective median theory, it's characterized by Ka, Kb, and Kc. There are 3 rigid phases, RABC, RB, and RC, where the system is rigid, and these are separated by these regions here, the surfaces here that I'm showing. And I can show you each of the surfaces corresponds, for instance, to a region, a phase boundary between 2 phases. And this blue region here, for instance, is a plane of rigidity percolation transitions, as I described before. And it terminates in a jamming line that's shown right here. So jamming occurs as a kind of a multi-critical point for the rigidity percolation transitions. Now, I'm going to skip this. This is just the bulk and shear moduli. The simulations and the effective median theory agree pretty well. And you can show the jamming point and things like that.
Sorry, can I ask?
Yes.
So contrary to my first question, now we are interested in the critical theory.
That's right.
So now this question about universality classes makes sense, right?
Yes.
And we are in 2 dimensions, and we have a degree of freedom, 0 or 1 at each link, indicating if the link is activated or not. Is it true, or that's...
A degree of 0, 1. You have, each bond is populated with probability
P.
P.
Either occupied or not.
Occupied, exactly.
So there is 0 or 1.
Exactly.
Right? So it's like an Ising model in 2 dimensions in some strange lattice, right?
But it's not, you don't have binary variables. It's an actual continuous mechanics system. So it does have elasticity. So these are actual springs. It's not right? Yes. So these are actual lattices. These are actual mass spring systems that you dilute the lattices. These are different kind of transition, yeah. Okay? So I have started by showing you this jamming packing of spheres or disks. And I've shown you how you can use these random elastic networks to describe this rather ubiquitous transition. And that's analytically tractable. And that clarifies the relation between rigidity percolation and jamming in general. So just to make the final remarks, started with this Anna Karenina principle. And I told you about these order systems that are all alike, and each disorder system is disordered in its own way. And I hope to have, it's my belief that it's not always the case that each disorder system is disordered in its own way. And that you can use ideas for the interplay between geometry and topology and disorder in order to get some general and universal behavior. Thanks very much for your attention.
Questions?
So can I think that you have a lattice and randomly you erase some connections, right? Like you were explaining.
Right. Yeah.
And then I have some position that still vibrates with springs, right?
Yeah.
So from that point of view, it looks a little bit like if I had an Ising model where I have a bunch of spins, but I remove some links at random, or I consider a random lattice.
Yeah.
Because from far away, the fact that it's continuous or discrete doesn't make much of a difference, right? From the infrared point of view. So is this in the same universality case as the 2D Ising model on a random lattice? On a random lattice, not on a fixed lattice, of course.
I don't know what the universality class is, but I don't think so. What the universality class is for the two-dimensional Ising model.
Yeah, on a random surface. This was studied by Kazakov, I think.
I don't know what it is.
Maybe it has this exponent 0 and 1 that you're showing.
So okay. Let me tell you something that maybe you give me the answer. The lower critical dimension, or the upper critical dimension for jamming is 2. So we are right at the upper critical dimension. So these exponents are mean field exponents for jamming. I don't know if that's the case for the two-dimensional Ising model in a random lattice.
Probably not. You're right. Yeah, that's probably not true.
Question? Okay, so let's thank Danilo. So the dinner, I guess everybody's invited, so it's Venus. It's 7. Yeah. So I think they forgot to tell the local people, but that's on. 7 o'clock.
Go back to the hotel. Sorry, I said 7. It's 7:30. So if you want to go together, I'll go to the hotel. So when we meet,
Oh, thanks. Oh, I got